Okay, we're continuing on here, chapter 13, chapter 17. I'm just going to start again. Chapter 17. So we're talking about electrochemistry, and we got into obviously our galvanic cells. And we sort of tied our galvanic cells into our thermodynamic properties. We talked about delta G is equal to minus NFE. And N is the number of moles of electrons. F is our Faraday's constant, 96,500 joules per volt per mole. E of our cell is again our cathode minus our anode. Or again, as we've been talking about many times, if you switch the sign there on the anode, then you should add them together when you take your kind of reduction and your oxidation potential together. We also saw a relationship between our E of the cell and our equilibrium constant, RT and F natural log of K. So again, if you got some cell voltage, you can figure out the equilibrium constant. Also, obviously, if you know the equilibrium constant, you can figure out the cell voltage between them. This obviously is from our normal sort of galvanic cell, cathode minus our anode in this case. Any questions on any of that stuff there that we were talking about previously? All right, then we're going to talk about sort of the effect of concentration on cell voltage, and that is what is sometimes referred to as the Nernst equation. And kind of taking our thermodynamics and equations together with our E of our cell gives us this guy right here, which is the Nernst equation. And you can kind of think of this very similar to sort of what we did with this equation here. We're going to talk about thermodynamics, really sort of our E of our cell under sort of non-standard conditions. So remember that when we sort of talk about standard conditions, where we see the little kind of knot that's usually drawn next to these thermodynamic sort of values, we're talking about temperature at 25 degrees Celsius, concentrations at 1 molar, pressures at 1 atmosphere. So I would say in most cases, probably pressures or concentrations, maybe something that's going to be the non-standard part of it. And that's sort of what you could think of this. So that E is under sort of non-standard conditions. So again, one of those things are not under standard conditions. This is our normal standard conditions, E of the cell, which again is our cathode minus our anode. The rest of these guys are still the same guys that we've been using, 8.314 version of our gas constant. Our temperature still in Kelvin. Our N is still the moles of electrons. Our F is still Faraday's constant, 96,500. And Q is still the same Q that we've used all over the place in these chapters. It is just like our K, which is the concentration of our products, divided by our reactants. Or obviously, if we're dealing with pressures, it would be the partial pressures of our products over our reactants. We still do obviously the same things we do with K. If there's a coefficient, we use that as the exponent and all those type of things. So we use a Nernst equation where, like I said, when something is sort of under non-standard conditions, and again, the kind of concentration and pressures are sort of the things that we sort of look at. We can use or kind of play with the concentrations or pressures, and you might be able to make a non-spontaneous reaction spontaneous by doing so. At 25 degrees Celsius, which is 298 Kelvin, we can also get a couple reduced down versions of this equation. One of which I think we'll see in lab today, which is this one I think that she used in the lab. And again, that's because the RT and F is our sort of constants at that point. If you don't want to worry about these two equations like we talked about with the other time we kind of saw them, you can pretty much just pop everybody into this equation, put all the numbers in, and you'll get pretty much the same answer. So if you just want to remember that equation, you could do that as well. By the way, if you can't remember the K equation there that we just talked about, it is also derived from this equation. So if we're at equilibrium, E would equal 0 and Q would equal K. So that would get you this equation being 0 is equal to E naught minus RT and F natural log of K. Bringing this whole thing to the other side gives you that earlier equation we just looked at. Also, why there is no negative here, where people always want to put a negative. So that is sort of how you get to that other equation that has the equilibrium constant. If you want to just remember this equation, and that's how you could get to that equation as well. So any questions on that there? All right, so let's take a look at one here. Give it a go. All right, so for the following reaction, is it spontaneous at 25 degrees if the concentration of iron is 0.6 and the concentration of cadmium is 0.01? There's some SRP values there, so see what you come up with in this case. Okay, let's take a look at this one. So the first thing that we should notice is when we look at these concentrations, they are not 1 molar, which means it is sort of non-standard conditions. And that means we should go to our Nernst equation, which is our E is equal to E naught minus RT NF natural log of Q in this case. Or again, you can use any of those other equations as well, since it's at 25 degrees. We do need to calculate our E of our cell, and that's going to be our, again, cathode minus anode. Once again, here we did get an equation, so we should look at it. So the iron here is going from +2 to 0. It is actually becoming more negative and is actually going through reduction. That means it is the iron that's our cathode in this case. And our anode is actually our cadmium, which is going from 0 to +2, becoming more positive as you go through that sort of number line, going from 0 to +2 cadmium, and our iron there going from +2 to 0 being reduced. So remember that because they did give you the equation, you do need to look and see what's happening to identify your anode and cathode. In this case, you would not take cadmium because they actually have the equation. Questions on that there? All right, so now that we know that, I am, again, in my case here, I'm not going to change the sign because I'm just going to subtract them. If you do want to change the sign, then remember you should add them. So I'm going to take my cathode, which is minus 0.44 volts, minus a minus 0.4 volts. That, again, will change the sign for my anode for me. And that's going to get me here a negative, if I can write it, try that again here. Just keep scribbling on it. I think that'll help us. Just keep putting lines on it. All right, try that again. There we go. I'll go with negative 0.04 volts. So under standard conditions, is this cell spontaneous? Is reaction spontaneous? Negative cell voltage means your delta G should be positive, right? As we have minus NFE. So negative will turn our delta G into a positive, which means this reaction would be non-spontaneous under standard conditions. Yeah. So we're not under standard conditions here. So we're trying to see if whether or not we can maybe turn this into a spontaneous reaction. So the rest of the stuff here is pretty straightforward. We have our R, which is our gas constant. We got our T, which we do need to convert into Kelvin, which will get us our 298 Kelvin. Our N in this case is 2, and that is because iron gains 2 electrons as cadmium loses 2 electrons. So that's balanced pretty much. So it's going to be 2 in that case. And our F is a constant of 96,500 joules per volt per mole. So if we go into here, we also need to calculate our Q, which is our products over our reactants in this case. And in this case, it would be the concentration of cadmium, which is our product, divided by the concentration of our iron in this case. And in that case, it would be 0.01 divided by 0.6. So that's going to get us something like, bless you, I believe 0.01667. So putting all that together now gives us our E is equal to minus 0.04 volts minus 8.314, 298 Kelvin divided by 2 moles, and our 96,500 joules per volt per mole. Natural log of basically what we just had there. All right. If we clean up the right-hand side there, this minus or subtract sign, we will end up with a minus 0.04 volts minus a minus 0.052, call it 6 volts. Subtracting those guys together ends us with a voltage here of 0.013 volts. First off, any question on the calculation? Is this reaction spontaneous? Now, it is. We got positive voltage. Not a heck of a lot, but we got a little bit of voltage happening there. So it definitely is going to be spontaneous in this case. First off, any questions on that calculation? Now, by playing with the concentration here, and in this particular case, having a greater concentration of iron versus cadmium, we were able to actually get a positive voltage, right? Now, out of curiosity, if we switch things around and what I mean by switching things around is we're just going to switch the concentrations. So if we use a little bit of room here too, I think. So let's just say if we kind of did it the other way around and made like the cadmium concentration the 0.6 molar and the iron too, the 0.01 molar. Really, the only thing that's going to change here is these two guys are going to basically swap places, and that would get us here. Our E is equal to minus 0.04 volts minus our 8.314, 298, our 2, and our 96,500. Natural log, again, switching it around would give us 0.6 up on top and 0.01 on the bottom. So if we put that in there, we will end up with minus 0.04 volts minus a 0.0526. And that's going to get us a cell voltage here of, call it negative 0.093 volts. Now, if I made, in this case, the cadmium concentration larger than the iron concentration, is my cell voltage now, is a spontaneous reaction now? It is not, right? Because we have a negative cell voltage. The reason for this is actually kind of like Le Chatelier's principle, right? In the first example that we had a greater concentration of iron over here than we did cadmium, right? And with a greater concentration of iron, that's going to mean more reactants are going to be present, right? And that should shift the equilibrium to the right. And causing that equilibrium to go to the right means that this reaction should actually proceed to the right and happen. And that should get you some positive voltage, right? Because you're actually making that guy go to the right. The second example that we did, where I switched it around and actually made my cadmium greater concentration than my iron, makes actually the opposite reaction happen. In this case, because there's more products, that should really kick off the reverse reaction, which means we're going the opposite way to our reactant side, which means that cell is not going to run, right? And that's why we get some negative voltage and it doesn't happen. So in a case like this, when we're doing something with like the Nernst equation and these sort of non-standard conditions, it does want to move from the higher concentration to the lower concentration based on like Le Chatelier's principle. And obviously the way the reaction is written, if that makes it go to the right, you should see an increase in the voltage. If you actually have a greater concentration on the right and it should go to the left there, I will actually cause the voltage to go back down the other way. So this is how we could play with the concentrations to sort of move a little bit of voltage, in sort of a non-standard conditions and non-spontaneous reaction. Any questions? All right, let's take a look at another one here. For the following one, forget about balancing it. Just calculate E of the cell and the equilibrium constant. So we're looking for E of our cell here. It's going to be our cathode minus our anode. So we do want to look at the equation, see what's going on. There's a lot of things going on here, but the chromium might be the easy thing to look at, +2 and +3. So again, that definitely is becoming more positive in that case, which means it's going through oxidation. And that means that should be our anode. By default, this guy here should be our cathode, as it's actually getting reduced. In case you're doing the math, something like maybe 2.5 to 2 in that case. It's where it's heading to, plus 2.5 to +2. So dropping a little bit there as it gets reduced in this particular case. So with that being said, we could go right into our E of our cell here. And we just said our cathode is the S4. So we'll go with 0.17 volts minus the minus 0.5 volts. Once again, I'm not going to change the sign because I'm subtracting. 0.17 minus negative 0.5, going to give us a 0.67 volts in this case. Again, if you can't remember the other equation, but you do remember the Nernst equation at equilibrium, E equals 0, Q equals K. So that gets you again, 0 is equal to E naught minus RT NF natural log of K. Bringing all that to the other side. It's going to give us E naught is equal to RT NF natural log of K. Just looking at the half reactions here, we see we perhaps need to balance out the electrons by multiplying that by 2. And that's important because then that should give us our N is going to equal to 2 in this case. Everything else there is pretty constant. So we have our 0.67 volts is equal to 8.314, which is our gas constant, our 298, our 2 moles, and our 96,500 joules per volt per mole, natural log of K. I'm going to basically here multiply what's on the bottom and then come back and divide by what's on top. I'm going to take 0.67 times 2 times 96,500 divided by 8.314 divided by 298. That's going to get me a 52.192 is equal to natural log of K. E of both sides there, going to give me a K here of, we'll go with 4.6 times 10 to the 22 in this case. Questions on that calculation? Things still agree like we would think they would. I see a positive cell voltage, which means this reaction should be spontaneous and heading to the product side. And because of that, I should have a large value there of K. So again, all those things should sort of agree with each other. Any questions on that there? All right, so obviously you need to be able to use the Nernst equation for non-standard conditions, be able to calculate K, E of the cell, and delta G related to it. Let's then talk about a little bit about batteries, which are, very much galvanic cells or a series of galvanic cells that have been sort of put together. Um, you're not going to need to memorize any sort of the equations or anything like that, but you need to know sort of similarities, I guess, in terms of batteries to traditional galvanic cells and some differences. So again, a battery can be a combined sort of galvanic cell. It's self-contained. There's no traditional sort of salt bridge that is used. So if we take a look at an example here of a battery, and I'm going to go with Duracell on this one, perhaps. It's a copper top. This is a dry cell, and the anode in this particular case is the zinc can or container that's in contact with this electrolyte solution. The cathode is the carbon rod that's immersed in the center. So again, we have sort of our zinc anode, right, to our cathode, electrons going out and about. Again, in your battery compartment, right, there's wires, right, where you put your batteries in. And again, that's used to use some type of power your device. This type of battery here gives you a voltage of about 1.5 volts. You can kind of think of like the electrolyte solution and all that are paste in here as sort of acting as sort of a salt bridge to kind of keep everything flowing correctly. Here on the anode reaction, we got 0 to +2, which is our oxidation. Over here on the cathode side, we do see our Mn, for example, here going from +4 to +3 in this case, getting reduced along the way. Now, all this type of dry cell will always sort of give the same voltage. There are different sizes, right? You can have C's, D's, right? Triple A's, double A's. They could just sort of last longer, this reaction, before it sort of dies down. You need new batteries. Another type of battery is a mercury battery. And mercury here is used a lot in medicine, electronic devices. It's a little bit more expensive. It has also sort of a stainless steel container with a zinc anode in contact with a strongly alkaline electrolyte. Alkaline is basic. So hence the KOH here, which is a strong base. Again, a strong base is a strong electrolyte, so that's going to, again, kind of act as sort of that salt bridge, keep everything going on. There's no change in electrolyte composition during operation, and that's really important because, frankly, that's what kind of keeps everything flowing and lasting for a really long time. Has a high capacity, a little less of a voltage here, 1.35. Again, kind of going from 0 to +2 here, +2 to 0 in terms of our reduction part of it here. This is one of the important things as we see with batteries in terms of long life. Also, rechargeability is having kind of no change, solids left over in their overall reactions. Really good for sort of long lasting and sort of the rechargeability as well. Speaking of sort of car batteries, that's a lead storage battery, is usually about 6 identical cells hooked together there in your car battery. Each one gives about a 2 volts for a 12-volt battery, which is, what you normally have. That's good enough to sort of start your ignition and your electrical systems in your car, unless, of course, you're late and your car doesn't want to start. It also has what we like to call battery acid, right? So it's got some type of aqueous sulfuric acid type solution inside of it as well. Again, sort of acting as sort of a salt bridge, keeping everything sort of flowing properly as well. It's rechargeable, which means the battery can sort of recharge itself. If you ever had a dead battery and they give you a jump start, they tell you to keep it running for a while, kind of recharge it, drive for a bit, and you might be okay without having to buy a new battery. We also have things like alternators and stuff like that, so we just don't drain batteries and stuff like that when we're driving. That kind of helps along with that as well. Here's sort of a cross section of a car battery, a traditional car battery. Don't cut it open, right? And you got your leads, your anode, and your cathode. And again, in certain cases, some cars that don't even actually have the battery in the actual engine anymore. Sometimes it's like in the back seat, in the trunk, and just like the little lead in case you need to jump, it's in the actual engine component. Here we see lead going from 0 to +2, again being oxidized in this case, and a little +4 to +2 action happening over here. Once again, we have a lot of solids sort of left over, which allows, this thing to sort of be recharged a lot and sort of keep it alive for a lot longer period of times. This is a solid state lithium battery. Lithium is a pretty light metal. It has a conducting carbon type of material like graphite that has holes for the lithium. So as the lithium gets oxidized, it can kind of migrate across this electrolyte to the other side. It can be recharged hundreds of times without any type of deterioration. It's also a really light one, while a lot of batteries for, say, tools and bones and stuff like that, or lithium and stuff like that, it's a really light metal, can be recharged lots and lots of times without a lot of degradation to it. This is a fuel cell, which is not a traditional sort of battery, but sort of functions the same way. In a hydrogen fuel cell such as this, you're actually shooting in hydrogen and oxygen into here. And in this case, our hydrogen is actually going from 0 to +1 being oxidized, oxygen going from 0 to -2 being reduced in this particular case. And this is what people had good ideas of making cars sort of run off of. Again, the idea there was that the only thing would be produced is water, which would be good, not so much pollutants or anything like that. We obviously did not really take off too much, although there's still, I think, a hydrogen cars still out there and stuff like that. I think Toyota, the Mirai, I think it's a hydrogen car. But we're now moved obviously to more hybrids and full battery type cars than say the fuel cell sort of situation. Any question on batteries? So, but yeah. What's that? Yeah, so what you need to know is you don't need to know any specific equations or anything like that. I'm not going to say, hey, give me the equation for like a Duracell battery or anything like that. But you need to know how batteries are similar and a little bit different than traditional galvanic cell. So obviously they function the same way, right? But one's more portable, no salt bridge, right? That type of stuff. Yeah. Other questions? All right, so talk a little bit about corrosion as well. And again, just kind of the idea of what corrosion is what you need to know. And we'll talk about a few ways you can kind of prevent it as well. So corrosion is really returning metals to their natural state. At one point, a fifth of iron or steel was produced to replace rusted metals. All metals that have an SRP less positive than oxygen gas are susceptible to going through oxidation and corrosion. And that's because if you have oxygen that has a more positive SRP than a metal, that means that the oxygen here is going to be your cathode and your metal is going to be your anode, which means electrons are going to head in that direction. And that's going to cause basically the oxidation of your metal, which is basically the corrosion of your metal. So any metal that, again, has that less positive SRP value than oxygen will go through corrosion. Now, spontaneously, by the way, that will give you really a spontaneous sort of reaction that's going to occur. Not all sort of corrosion is necessarily a bad thing. Sometimes corrosion can actually produce a layer that will actually protect the metal underneath from further corrosion. Aluminum, for example, will form this aluminum oxide that, although it did corrode, will actually protect the rest of the metal that's underneath there. Now, iron does the same thing. The problem, though, with iron is rust will tend to fall off, and you could kind of rust right through a piece of metal as it falls off. New metal's exposed to corrosion, and that gets rusted out and then falls off, and new metal before you go through it. Copper as well can go through corrosion. It makes that expensive patina look that people like. Silver can tarnish. Sulfide. Now, gold that has actually a SRP value of 1.5 actually will not go through any corrosion, and that's because when gold and oxygen get together, gold's actually more positive, and gold is actually the cathode. And in that case, oxygen would be the anode. So there's no sort of oxidation happening to gold in this particular case when they get together. Now, the reason we do get sort of rust is steel has really non-uniform points on it, and that's great places for moisture basically to sit. And those are really three things that you need for rust to form: a little bit of iron, a little bit of moisture, and some oxygen. And you got pretty much all the makings for rust to happen. So iron actually rusts in a two-step process. It actually becomes iron 2 first, and then those iron 2 travel through the surface there, and it ends up as iron 3 oxide, which is rust. So it actually gets oxidized all the way down to iron 3 in this process. And as you can see here, this sort of points in there where moisture can sit, air supplying some oxygen. We have our iron getting oxidized, and before you know it, we have rust, which again, the problem with it can fall off and obviously cost lots of money to replace. As if you've ever seen a rusted piece of metal, pretty much you can almost put your finger through it. Sometimes it's so rusted out, there's not very strong at all. Now, there are ways we could prevent corrosion. So some ways that we could do that is application of some type of coating. We could use some type of paint. You could paint the metal. There's Rust-Oleum paint, right? Which the idea there is to protect it from rusting. You could also use chromium or tin to plate the steel. They make this sort of effective oxide layer that protects the metal underneath. Galvanizing with zinc. And zinc is more active metal than iron. So when you get zinc and iron together, by doing this, it's actually iron that becomes more positive. So iron becomes the cathode and zinc becomes the anode. So all the oxidation and corrosion will actually happen on the zinc, again, protecting the iron from doing that. As it says there, zinc sort of acts as a sacrificial sort of coating that allows the protection of really the iron. Alloying is another way that you can prevent corrosion. You can have some other sort of elements in there which sort of change the reduction potential of that particular metal into something that's more like a noble gas, which noble gas are noble metals. Noble metals are non-reactive, and that will kind of make it very much non-reactive. Another way that sometimes this sort of protection is used, you could do cathodic protection. For example, you could take magnesium that's connected to by a wire to a tank or something like that that you bury under the ground. Obviously, you bury this tank under the ground, there's a lot of moisture and stuff like that. It could just go through corrosion. But magnesium is a better reducing agent than iron, and reducing agents are things that get oxidized. So since magnesium is a better reducing agent than iron, it is the magnesium that goes through the oxidation. Again, the iron will act more like the cathode in that situation and not go through oxidation. Titanium's used in ship hulls to prevent sort of saltwater damage. Here's the idea. So if you're like at a gas station or something like that, you don't have to dig up your tank every 2 weeks. You have this magnesium here. Again, all the bad stuff happening on the magnesium. The iron tank doesn't go through any sort of sufficient amount of corrosion, and it's able to basically be there for a good period of time before it might need to be replaced or repaired. Any question on corrosion? So for corrosion, you need to know sort of what it is, a couple of ways to protect it, along with what a battery is and how it's similar and different to a galvanic cell. Probably question 7 on the exam. I imagine that would be probably that question. Any questions on that there? All right, we're going to lay it up there for today. We